All right, this is section 8.4 and lines. And so let's look at a line, just kind of thinking about it in two dimensions. So here's a line, and we tend to think, oh, 2 points determine a line and so forth. Now, why might that be? Well, let's think about it in terms of vectors, what's going on. Okay, I've got that vector, so that position vector for that point, and maybe this is A, point A, and position vector A. And then out here I've got B and point B. So, here's A, here's B, and then their position vectors. And notice along this line, it really doesn't matter which one of these two vectors I use, but if I look at this vector here, that vector, well, I took A plus something and got B. Well, A plus B minus A is equal to B. This is the vector B minus A. And now it's not sitting at the origin, but again, this is the idea. We can use our intuition and kind of move these things around. But notice this line is parallel to that vector B minus A. And if we want to hit a point up here, we maybe about there, we need to take a vector about twice that long. If I want to hit a vector or a point about there, I need to take the negative of B minus A. So again, remember, all these vectors that I'm talking about are parallel to this B minus A, and so I want just this set of vectors that are parallel to B minus A, but I need to sort of offset them by A here. Now notice I could also offset them by B. It doesn't really matter, but all points on this line I could describe by their position vectors, and those position vectors would be A plus some t times B minus A. Okay, and notice that this has an analogy to point slope, right? How do I define a line? Well, usually we'll say, well, you need 2 points. Well, why do we need 2 points? Well, we need 2 points because we need a point and a slope, and we use that second point to get the slope. Okay. We need a point, a position vector there, and then a slope, a direction vector there, and we take all multiples of it. So they define a line. Okay, define a line. Now, they say in E3, okay, it's the set of all points satisfying this, so I don't really know why they went to E3. I would say, actually, I would just say a line in Rn in general. We're just really interested in R3 in this chapter, but define a line in Rn as all points satisfying and now see, we're going to switch to the position vector notation. All points, I should say P, satisfying that their position vector is equal to some initial position vector plus t times some direction vector, where t is any element of the real number, so all multiples of that direction vector x. Okay, so that is a line. Okay, and their theorem 8.4.1 says if A and B are distinct points, there is one and only one line containing both A and B. Okay, now notice this, what I want to point out here is this is talking about existence. Okay, there is one line, and uniqueness. Only one line. Okay, so this theorem speaks to the existence and uniqueness, and they say that our line then is P equal and they're going to do it a couple different ways. They're going to say 1 minus t. I like this, that they're doing that, plus tb. So they give that form. And what I like is, in this case, in this form, if 0 is less than or equal to t is less than or equal to 1, then P is between A and B, okay? Or equivalently, the points P and then the points A and B. So it's actually in between them. And then they rewrite this as A and then plus T times B minus A. So either form is fine, but I really like that the authors use this particular form because, again, if t is between 0 and 1, we call this a convex combination. And that's a nice phrase to see, and when you start talking about this geometry and so forth, it's a good thing to realize, is that when I take this form here and t is between 0 and 1, which is also true then here, t is between 0 and 1, I get a point that's in between the points A and B. Now, again, these are vectors, so you could write these each as a separate relationship. You could say if you have A is the point x1, y1, z1, and B is the point x2, y2, z2, then instead of writing it in vector notation there, you could write, well, x is x1 plus t times x2 minus x1, and y is equal to y1 plus t times y2 minus y1, and z is equal to z1 plus t z2 minus z1. Okay, so we call these parametric equations. And so if you've done Calc 2, definitely if you've done Calc 3, but likely even if you've done Calc 2, you've probably looked at parameterized curves. And so this is just, you can think of that straight line as being parameterized in T. And let's see. I think I'm going to stop it there, and then we'll maybe do another video.